Okay, so we are still discussing how to find maxima and minima of functions of more than one variable. Now, so last time I showed you that there is something okay, so we have a function of two variables, and what we want to do is we want to find first local extremas. We will today also discuss how to find absolute extrema. Now, last time I showed you already that if you have a local extrema of such a function and the partial derivatives exist, then both are equal to 0. So that's how you can find points where you might have a local extrema. Now, because of this result, which is similar to what we called Fermat's theorem last semester, we can define what we called critical points last semester. So critical points are points where either at least one of the partial derivatives does not exist, or if both partial derivatives exist, if you plug in the point, you get for both that they are equal to 0. So these are the critical points. And the critical points, as last semester, are the candidates for local extrema. So if you have a local extrema, the set of local extrema is contained in the set of critical points. But the critical point is not necessarily a local extrema, as we have seen looking at some examples. Now, the way you decide whether at some point you have a local extrema or not is using you look at something which is similar to the second derivative, so second derivative test. But of course, for a function of two variables, you have if you look at the second derivative, if the second derivative is the partial derivatives, you have 4 of them, and you have to take those 4 numbers suitable into account in order to decide whether you have at some point critical point, a local maximum, local minimum, or nothing. And last time I showed you already, or I wrote already the main result on the blackboard. So we assume that this function is that the partial derivatives, assume that the partial derivatives, the second partial derivatives exist in a disk, exist and are continuous. And are continuous in a disk with center AB. And AB, assume that AB is a critical point. Moreover, so AB should be a critical point, so the partial derivatives should be equal to 0. Then we define a quantity which we call D. So this is fxx, fyy, minus, and then the mixed partial derivative square. And now you have 3 cases. Case 1. D is larger than 0, and then you have to look at fxx. So fxx is smaller than 0, then you have a local maximum. The second case, D is larger than 0, and the second partial derivative, both time with respect to x, is larger than 0. So in this case, you have a local minimum. And you have a final case where D is smaller than 0. In this case, you have nothing, so no extrema. Okay, so you have those 3 cases. You have to note that the case D is equal to 0 is missing. So here, if you look at the first 2 cases, it looks like fxx is equal to 0 is missing as well. But if fxx is equal to 0, then this is equal to 0, and t must be negative or 0. Okay, so actually, for if t is larger than 0, then fxx cannot be equal to 0. Cannot be equal to 0. Okay, so actually, fxx is equal to 0 is not missing here from those two cases. But the situation which is really missing is t is equal to 0. Now, you should also notice that in this case here, no extrema, even so we know that here we have no extrema, but still, if you look at in our textbook, still you have a certain special property here at AB, namely the surface or the graph of this function must cross the horizontal, because in AB you have a horizontal tangent plane, and in this case the graph must cross the horizontal tangent plane. Okay, this is not this makes this case also special. Okay, so you have here so-called saddle point. You understand what I mean? This is no extrema, but still somehow special. Okay, so what is so special? Maybe I give you an example just so you see what is so special about this case. For instance, this is a function which we can easily depict. Okay, so this function is a cylinder. So the graph is a cylinder. So you have something like so the graph looks roughly like this here. Now, you see, for instance, easily that the critical point, there are many critical points here, okay, because the partial derivatives always exist. The partial derivative with respect to x is 2x. You equate it to 0, it's equal to, it gives you x is equal to 0, but the partial derivative with respect to y is equal to 0, so y is arbitrary. Okay, so you have many critical points here. All the critical points here in this case are the y-axis, okay? But you see that, for instance, if we fix one critical point, this one, okay, you see that the tangent plane here at this point indeed is horizontal, but the graph does not cross the tangent plane, okay? So this, in this point, you do not have a local extrema, of course, but you are also not in this situation, no saddle point here, okay? So this situation is more special, because this situation, the saddle point situation, for such a situation, the graph has to cross the tangent plane. Okay, here is not the case. So without doing any calculations, I know here for this example, the t must be equal to 0. Because if t is smaller than 0, then I would have a saddle point. I don't have a saddle point here. Okay, so this kind of saddle point doesn't mean it's just a point where the tangent plane is horizontal, but no extrema. It's not so easy, okay? Here, for a saddle point, the graph crosses the tangent plane. This is not the case here. So here, all those points are not saddle points. Okay, so you have to observe this. Maybe this is not so obvious. It doesn't come out so obvious from our textbook, from the explanation in our textbook. Okay, so any questions to this? Actually, the proof of this result is not very complicated, and if you look at the proof of this result, it's also more. It's also clear why you need these assumptions here. So why do you need that the second partial derivatives are because it looks like its existence is enough, but you see that they must even be continuous inside the disk. Okay, this you have to look at the proof that you know why this is required. Now. For the proof, because the proof is not very complicated, so what we do is, okay, so we look, for instance, at the following function. Maybe f is not a good name. So we fix a unit vector. uv, or call it hk. Now look at the function g of s, which is f of. So you leave a, b in a special direction. Okay, the direction is a plus given by this unit vector. So you have a plus sh and b plus sk. Okay, if we take here the first derivative, the derivative of g with respect to s, and then we plug in s is equal to 0, what we get is the directional derivative of f in direction of u at a point a, b. Okay, so this is the derivative of g at 0. Now, what we have to look at is at the second derivative, okay? Because we want to know locally at AB. So the idea is very simple. We are standing at AB. We want to decide. We know at AB that the tangent is horizontal. Okay. We want to decide whether at AB you have a local extrema or not. So what do? We first choose a direction, and then we walk on the curve along this direction. And we prove that all those curves, no matter how we choose the direction, all those curves are, for instance, for this situation, let's say this one, are concave upward, then you are done. Okay, because then you are standing at AB. No matter how you leave, you always you check any direction. Okay, you leave along a curve which is like you choose a direction, you leave the point AB along a curve in this direction. Okay, and if this curve is always concave upward, okay, this means that all those curves must lie above the horizontal tangent plane. Okay, so in this case you have this certainly means that at this point you have a local minima. Okay, so what we have to look at is the second derivative of this function. Okay, so we compute the second derivative with respect to s, of course. Now for this we have to use the chain rule. So what we have to do is we have the first derivative of this function here. The derivative with respect to s, but this we can easily compute with the chain rule. So first the partial derivative of f with respect to x, and then we plug in a plus sh, b plus. Yeah, I don't write what I plug in, because anyway I plug always in I plug always in this expression here. So the partial derivative here times, but if we compute here the partial derivative with respect to, or the derivative with respect to s of this function, so first the partial derivative with respect to x times the derivative of this here, which gives you a h, plus, and then the partial derivative of f with respect to the second coordinate, and then the derivative of this here with respect to s, which gives you a k. And then you do the same once more. But you have to take into account that this, of course, is a constant, but here this is a function of two variables. So again, you have to use the chain rule. So what you get is, okay, so first the partial derivative with respect to x, which gives you fxx, and then you have another h, so h squared, plus then the partial derivative with respect to y, which gives you a k, but here you have also the mixed term, because here you have to compute the partial derivative first with respect to x, and this gives you also a h. Okay, so you have twice f x y k h plus, and then you have to here to compute the partial derivative with respect to y, and then you get another k, so k squared. Okay. Now, if you have such an expression, okay, what we can do is we can complete the square. So we take out fxx, then we have here fxy over fxx, and we complete the square. So we have h plus, and then we have fxy over fxx, and we have k square. Okay. For this, of course, you have to assume that fxx is not equal to 0. But for instance, if we are in this case, let's say we discuss this case. If we are in this case here, then fxx is larger than 0. You have to note in point AB, okay? But we assume that fxx is continuous inside the disk. So this means that you can certainly find a very tiny disk so the disk is not necessarily the same size of this one, even smaller disk, such that AVB is for all values in this disk is positive. Okay, this is the continuous property. So this is not on a sufficiently small disk. We certainly can do this. What else? So what is left? Plus. You see. So what you have is k squared over fxx, and you see the rest is exactly our d. Okay, because you have here, if you take out the fxx, you have here fxx times fyy, and you have to subtract, because here you have one term, one additional term, and you have to subtract the additional term, which is exactly the fxy square. And now the only idea is, okay, if you look at this here, so this is certainly positive, okay, and you see that if you assume this here, then this is positive here, and this will be positive, and if you are in this case, then the d will be positive as well, so everything will be positive. Okay, so you see that if you are, for instance, in the second case, then this tells you that you have to notice something. Actually, I have to write here the fxx has also an argument. Okay, so this just holds in 1 point for 1 point, namely AB. Okay, but because of this continuous property, this will be still true if you leave AB just a little bit. Okay, so in other words, there will be a disk around AB, which might be smaller than this one, such that those two conditions are satisfied. Also inside the disk, and that's why we need this continuous property. Okay, so because of this continuous property, this will be larger than 0 on a sufficiently small disk. With center AB. Here there should be a E, right? I'm not so sure. I always forget whether there is a E or not. This is a long-standing problem. Is there one or no? Sometimes there is one in English, sometimes not. Okay. Anyway, you know what you mean. Maybe there is a E. Okay, I'm never sure. This is a long mistake, which I already made in the high school. Okay, so because of this, but this is not essential whether here is an E or not. This here is larger than 0. Okay, because of those. If we are in case 2, okay, I'm talking about the case 2 now. This will be larger than 0 on a sufficiently small disk containing AB, which means that if because we leave here AB in a certain direction, which means that if we leave in this direction, the curve on which we are walking is concave upward, and this does not depend. This argument does not depend on the direction. Okay, so no matter how you leave, you're standing at the point AB. No matter how you leave, you are always walking on a curve which is concave upward. But of course, you leave here because you could object. I just leave along certain directions which are lines projected down on the xy plane are lines. Okay, but of course here for the point, in order to deduce that the point AB in this situation is a local minima, this will be enough. Okay, this finished already the proof. So this is not, so maybe I didn't write too much details, but this just gives you an idea, okay, why that this result actually not complicated, okay. It's not so. So essentially, what we do is we use a similar idea as last semester, namely we try to, because also last semester for the second derivative test, what was essential was to figure out whether the curve is concave upward or concave downward in order to decide whether we have a local extrema at some critical point. This is just the same idea. Okay, so maybe let's look at an example to see how to apply this result. The example is the following function: f of x y is equal to 4 plus x to the cube plus y to the cube minus 3xy. Okay, and what we want to find is local extrema and saddle points. Okay, so find all local extrema and saddle points of this function. Now, the first thing which we do, the first thing we have to find is critical points. So what we compute is the partial derivative with respect to x. So this will give you 3x squared minus 3y, and the partial derivative with respect to y, but everything is of course symmetric, so what you get is this one, and you have to equate those to 0. Normally, the equations you get here, the system of equations you get here is not always easy to solve, because this is not a linear system. Okay, so it can be very complicated for a function, for a more complicated function. Most of the times you have to use Maple in order to solve it. So, but here it's easy. So you see that x squared is equal to y, and from here you see that y squared is equal to x. So from this you easily get that, for instance, you plug in here, you get x to the 4th minus x is equal to 0 for x. So this gives you x times, then x to the cube minus 1, and this is x minus 1 times x squared plus x plus 1 is equal to 0. So you see from here you get two solutions. X is equal to 0 and x is equal to 1. And once you have these two solutions, you plug it in here, so you get y is equal to 0 for this one. So this is a pair of solution, and for this solution you plug in and you get y is equal to plus minus 1. Okay, now normally what we do is, okay, let's make a small table, or let's compute. We have to compute the second partial derivatives. So for this one, so fxx is equal to 6x, then fyy is equal to 6y because of symmetry, and fxy, of course, for this example is equal to fyx is equal to minus 3. Okay, so from this you see that d is equal to 36 x times y minus 9. So you see, in this case, so for this point, x is equal to 0, y is equal to 0. So the first point is x is equal to 0, y is equal to 0. So for in this case, d is smaller than 0. Okay, so here you have a saddle point. And then the other one is x is equal to 1, y is equal to plus minus 1. So here plus 1. So here d is equal to 25. So we have to look at, so larger than 0, so we have to look at fxx, which in this point is 6. So what you have is a local minimum. Then you have the point x is equal to 1, y is equal to minus 1. In this case, d is smaller than 0, so you have a saddle point. That's why I was surprised, because actually this should be very symmetric. And it would be strange if there would be a different behavior. Because this would break the symmetry. Okay, so this. Okay, thank you. Now, but let's look at Maple. Okay, so let's just plot the curve and let's check whether we see this here. So whether we really see the saddle point at this point here, and local minimum at this point here. Now, this will already this will also show you that if you use Maple in order to investigate functions of two variables, it's not so easy, because Maple, in particular, this plot 3D comment. Okay, for this comment you have to choose as the region over which you plot the function. You have to choose a rectangle, and in particular, if the function is this kind of is very restrictive. As we will see, I plot first, and then I will explain what I mean by this. So we have this function here. Minus 3 times x times y, and let's choose for the plotting rectangle. So let's go from what is interesting. So let's choose, for instance, from 0.5 to 1.5 x, so that we capture both points, and y. For y we can choose from, let's go from, or let's make it symmetric, but maybe it's not so good to make it symmetric if we look at this one. Okay, but let's go from 0 to 2. You see from this here, you see nothing. Now, because we are investigating local extrema, so what we certainly should do is we should draw a coordinate system. But you still see nothing, right? You agree? It's like, okay, it looks like, okay, nothing, no saddle point, nothing. You cannot see anything from this kind of graph. One of the reasons why you see nothing is because you look at this, because one function value as x and as x is getting small and y is close to 2, so this function value is much too large. And if the surface is behaving like this here, of course, you cannot see what is going on here in this area, because this one is much too large, and what you see is just the behavior behind. Okay, so here it's crucially depends. If you want to discuss something like this, it crucially depends how you draw things. And here's x, and here's y. So of course you see some symmetry, but like at 1, 1. There should be a local minima. You could kind of guess it, but okay, it's not so obvious, right? It's hard to see. Now, and as I said, the problem is here. This function value is too large, 14. Okay, so you would like Maple is not drawing this function value that large. Okay, of course you can kind of restrict it, but then you might lose. So what can we do? So you see that the problem is if y is getting large and x is small. Okay, so we should maybe plot x from 0.5. Also here it's not clear. Okay, of course you can also, if you do not like that I plot everything not symmetric, so you can choose something like then it's even. Okay, now maybe okay, so you might agree. Okay, it's not so easy to see something from such a plot, so it's very essential here how you plot things. But something which sometimes helps is, in particular, if you have function values which are too large, which you consider too large, then it's sometimes better to use the implicit block comment, because the implicit block comment, for the implicit block comment, you give an equation. Of course, here you have given the function explicitly equal to z, but you can give it as an equation. And for implicit plot, you can not only restrict the domain for x and y, but also z. And then you can, this you can normally use in order to understand a function much better. So but this implicit plot is not part of the standard plot package in Maple, so I have to load it in. So this is with plots. Now, now you have a comment, an additional comment, which is called implicit plot 3D. This is kind of better here, because you can now also specify. So you have to give an equation now. So the equation is this one. And you can also restrict set. So set, let's say from, what is a good, so let's say from 0, looks like, yeah, let's say from 0 to, let's say 5. Where is this one? No, now I changed. So this one. Now you have, but now you have another problem. Now the problem is it looks very ugly. So you have to. The problem here is that Maple chooses a certain amount of points, okay, and plots the function for these points, and then between the points, Maple is using a plane to connect them. Now, but this is not a problem because you just add some more points. Which you do by the grid comment. So the grid comment, you can, the grid is what you see here. This is the grid which Maple uses at the moment. So I just make the grid finer. So I use something like 20, 20, 20. Now you see, okay, now it's better. In particular, you see now that there is a local minimum. Okay, this is something which you haven't seen at all before. Because once more, the problem before was that I could just restrict the domain for x and y, okay, and the set was then given by them. But for some point, okay, the function value was much too large. But if you have very large function values, okay, then everything else, if you have another part where the function values are quite small, okay, then this just looks, you cannot see any properties from this. But now you can see it much better. But in order to find here the behavior, okay, of course, what we need is the reason why we could figure out that at 1, 1 is a local minima is because we knew it, and now I plotted it such that you could see it. Okay, but this should demonstrate, okay, that for functions of 2 variables, okay, this plotting them can sometimes be quite tricky. Okay, and I mean plotting them that you see some properties. Another example is the one, I don't want to do the computations for this example. You can find this in our textbook. There is one more example, a given function. And you just have to do the same as here. So figure out where are the local extrema and where are the saddle points. Now, this function is more complicated. You have this here 10x squared y minus 5x squared minus 4y squared minus x to the 4th minus 2y to the 4th. You can find this example in our textbook. Now, if you just do the same as to what I have done for the previous example, then you figure out that 0, 0 is a local maximum. Then you have more local maxima. So those 2 points here are also local maxima. And you have a saddle point, 2 of them. this is one of the examples in our textbook. What is the number? Example 2 or example 4. I just want to show you that also for this example, it's quite complicated to plot it, such that you can really see something from the plot. And this should help you to understand, because it looks like, if you read the textbook, it looks like, okay, because the plot is added for every example, and it looks like, okay, if I have a graphing device, I just plot it and I can see the properties. But this is just to demonstrate that it's not so easy to plot such graphs of of functions of two variables. So here we have 10x squared x times x squared times y minus 5 times x squared minus 4 times y squared minus x to the fourth minus 2 times y to the fourth. Now, what are we going to choose for the viewing rectangle? So, of course, we would like to see all this information here. So for the x, we can, for instance, we can choose from minus 2.8 to 2.8, or maybe minus 3 to 3. And for y we so we have to capture all those properties. So we go from minus 0.5 to 2.5. Now we also have to add a coordinate system. Boxed is always good here. Y axis. You see, if you compare this, you see, you might guess that you have local maxima here, where you have these kind of ears. Okay, but you see that at 0, 0, there should be a local maxima as well. 0, 0, this you cannot see because it's too flat there. Okay, and if you compare this with the plot in our textbook, okay, the plot in our textbook looks much more pretty than this one. Okay, so it's not so easy. You shouldn't be deceived by this. Okay, if you see such a plot in a textbook, the author had to spend some. This certainly took some time to get such a nice plot of the surface. Okay, and you certainly need an analysis before you can make such a nice plot in order to see all the main properties. You see here again, the problem is that here the function is much too small. Okay, because the function is very small here, and on the other side, okay, you cannot see the maxima at 0, 0. So that's the main problem. And again, implicit plots 3D should work better here. I'm not sure whether this is the best possibility. Okay, so maybe if you play a little bit around, maybe there is a better one. This is just the only possibility I can come up with. Okay, so let's say for this we have to, so at this maxima, at this local maxima, it's also, you can also find this in our textbook, the function is 8.5, so we should plot it something like, let's say from minus 10 to 10 is maybe a good range. Of course, the implicit plot 3D comment compared to the plot 3D comment, of course, has a disadvantage, namely the grid thing. Okay, so it looks always ugly. But you see now, if you restrict here the range for set, okay, it looks already much better in the sense that, I mean, the plot is ugly. Okay, it doesn't look better, but in the sense that you can see the properties much better. In particular, you can see that over there you have a local maxima as well, where you have this kind of nose. And of course, if you do not like this, if you think it's too ugly, then you can again just choose a finite grid. Okay, now it's better, but now it's better. But again, Maple has some problems here, where you have this kind of two wings. Here Maple has some problems, but now you can see that at 0, 0 there is a local maxima. If you do not like this grid here, okay, because this grid also doesn't look very pretty, okay, If you do not like it, you can take it away and so on. You have all kinds of possibilities. I don't know, I forgot the comment and I don't want to search for it, but it's possible to take the grid away from the surface, then it doesn't look so packed. Okay, so you see that this should convince you that calculus is necessary for functions of two variable in order to find local extrema. Of course, for functions of one variable, you have the same problem. If you do not choose the right range for x over which you plot the function, if you have a function of one variable, just of x, then you might not see some of the properties, of the main properties of the function either. Okay, so you have the same property, the same problem, but you see it's much more tricky here for functions of two variables, okay, because you have two dimensions which you have to care about. And normally, if you want to understand the graph of a function of two variables, what you do is normally first you use calculus in order to find out the main properties, and this helps you to decide to find the right plotting window for the function. And if you still cannot see the properties, you have to restrict some of the values. Now, another type of examples, of course, we can use now this kind of approach also in order to solve optimization problems for functions of two variables, something we couldn't do last semester. So, for instance, if you have the following example, rectangular box is made from (12 square meter) cardboard. Find the maximum volume of such a box. This is different from slightly different from the example you find in our textbook, because in our textbook you have a rectangular box without lid, but now you have the lid. So you have a box. And what is given is the surface area of this box. So the surface area is equal to 12 square meter, and you should maximize the volume. Of course, everyone will guess the answer is a cube. But now we can show it. For the volume, so if this is x here, this is y, and this is z, then the volume is x times y times z. And the surface area, so from this condition we get that x 2 times x times y plus 2 times y times z plus 2 times x times z must be equal to 12. Now, or in other words, we can erase the 2 and we get this here. Okay, so we have here, this is our object, this is our function which we have to maximize, but we have only, and this is the difference to last semester, we have only one condition, okay? So we can, using this condition, okay, we can remove one, we can get rid of one of the variables, but we are still left with a function of two variables. But this is no problem, because we know how to discuss now extreme values of functions of two variables. So the first thing is we maybe get rid of, let's say, z. Then we have 6 minus x times y over y plus x. Now we plug this into the original function, so x times y. Now we have to find the critical points, so we have to take derivatives. computed those derivatives. I'm not going to do it once more. I could also use Maple to do it. Minus 2xy minus x squared over x plus y squared. And for the partial derivative with respect to y, I know there should be a mistake here. Wait a moment. This should be 6 here. Because here the dimensions are slightly different. Okay, so we have here x squared, and here we have 6 minus 2x times y minus y squared over x plus y squared. Okay, and we have to equate both to 0. And we have to find all solutions of this. Of course, one solution, you see one solution, x is equal to 0, but this doesn't make sense because we want to maximize the volume. X is equal to 0 would give 0. Okay, so this must be equal to 0, and this must be equal to 0. So we see that 6 minus 2xy is equal to x squared, and 6 minus 2xy is equal to y squared. Okay, and from those two you get that x squared is equal to y squared, or you get that x is equal to y. Okay, now you can plug this in here. First you have to find, okay, so you plug it in, for instance, here in order to find the y or the x. It doesn't matter. So let's maybe find first the x. So we have 6 minus 2x squared is equal to x squared. So this becomes easy. So x squared is equal to 2. So we see that x must be equal to square root of 2. So from this here, y is also equal to square root of 2. And now you plug this in here. So z must be equal to 6 minus, you see 2 over twice the square root of 2, which is 2 over square root of 2. But this is square root of 2. Okay, and this confirms that x must be equal to y must be equal to z. So you see that so you see that if you have given the surface area, of course this is true in general, no matter which number you have here, if the surface area is fixed and you want to maximize the volume of a box, the maximum is achieved for the cube. Okay, and you have, of course, you can use this in order to solve similar optimization problems. You have many examples in our textbook, and we will do some of the examples for the assignments. Any question? Actually, I forgot to check because I got a solution. I forgot to check whether I have really a maximum at this solution. This, of course, I have to do as well. But here it should be clear from the problem setting that we have a solution to this optimization problem. For optimization problems, it's quite often that from the problem setting, you know that there must be a solution to the optimization problem, and you do not have to check for the solution the solution you get is really a solution in the sense that because what I computed here was just a critical point, and I would have to check whether there is really a local extrema at the critical point. But this you don't have to do in this case because from the problem setting it should be clear. Now, so far we have only discussed how to find local extrema. So how about absolute extrema? Last semester we had also a method to find absolute extreme values for a continuous function. This maybe you remember, so whenever we have a continuous function on a closed interval, then we have this so-called extreme value theorem, which tells us that such a function must have an absolute maximum and an absolute minimum. This is something you might intuitively or heuristically you might guess this, but we haven't proved it actually last semester, and it's not so easy to prove this result. This is a so-called extreme value theorem, but this is a useful result because it gives us an easy method how to find absolute extrema for a continuous function on a closed interval. Namely, the only thing we have to do is we first have to compute all the critical points. Then we compute the function value at the critical points, and we compute the function value at the two boundary points, and we just pick the largest one and the smallest one. The largest one must be the absolute maximum, and the smallest one the absolute minimum. For this, of course, for this method to work, you need that the function actually has the absolute maximum and absolute minimum. Otherwise, this method might give you a wrong result. Now here also for functions of two variables, we have a similar result, but in order to state it, we have to discuss first what is the analog of a closed interval here in this setting. So for this, we make the following definition. Now, we call it a set D. D is called closed if it contains its boundary. I will explain in a minute what this is supposed to mean. And D is called I have to add here called. And D is called bounded if it is contained in a sufficiently large disk. Okay, so for instance, if you look at the set D, which is given by the most easiest example, maybe the disk, the unit disk. Okay, then this set is certainly bounded, is certainly contained in the disk. Okay, you can either choose this one, or you can choose even you can also choose a larger one. So bounded, roughly speaking, means that the set does not extend to infinity. Okay, and closed means all the points on the boundary. The boundary should be clear what it's supposed to mean. The boundary is this here. Okay, all the points on the boundary are contained in the set. So it should be. So if I remove one point here at the boundary, so for instance I remove this point here at the boundary. Okay, then the set is still bounded but not closed anymore. This is a very sloppy definition because actually in mathematics we first define boundary points, then we define the boundary, and then we define closed. Okay, but this is just a matter of writing things down precisely. Now, the importance of such sets, so sets which are closed and bounded, is the following. If you have a function which is, they kind of replace the closed intervals. So if you have a function which is continuous on a set which is closed and bounded, then such a function, it can be proved that such a function must have an absolute maximum and the absolute minimum. So this is the extreme value theorem. For functions of two variables. continuous function on a bounded and closed set D has an absolute maximum and an absolute minimum. This is similar to the extreme value theorem we have seen last semester, and also this result we are not going to prove it, because the proof actually it looks very trivial, the result, but the proof is not so easy. Of course, you would if you hear this result, everyone will believe it's true, but the only problem, more or less, in proving such a result is how to write down an argument which is convincing, okay, more than just saying, okay, I believe it, okay, and for such a result, it's not so easy, surprisingly, because the result looks very, very easy, and it's also easy to guess that this is true. But for us, the important thing is we can use this result, okay, the extreme value theorem for functions of two variables, in order to find for a function, if you have given a function on a bounded and closed set D, this gives us easily a method how to find the absolute maximum and absolute minimum. Namely, what you do is first you find all the critical points of this function and compute the function value at the critical points, and then you check the boundary, the behavior on the boundary. And so kind of you can imagine you can kind of imagine you compute the function value on the boundary, but this essentially in many problems is boils down to a problem of a function of one variable, which we can already solve, and then you just take the largest value of all the function values at the critical points and all the points at the boundary, and this must be the absolute maximum, and you take the smallest value of all the function values at the critical points and at the boundary, and this must be the absolute minimum. So this replaces what we called last semester the closed interval method. So maybe the best way to explain this method is looking at an example. But you should understand that this result here is the basis of this method. For instance, okay, so let's say we have the following function, 4x plus 6y minus x squared minus y squared. And let's say the domain is given by okay, so what we have here is a rectangle. So D is a rectangle. You see that D is also closed because essentially because you have here smaller equal, not smaller. If you have smaller, then it wouldn't be closed. So you see you have here the rectangle with side lengths 4 and 5, and what we want to find is the absolute extrema, absolute maximum, and absolute minimum of this function on D. Now, since the function is obviously continuous on D, we can use, we know that absolute maximum and absolute minimum must exist. Now, what we do is, so the first step is we compute the critical numbers. So for this, we have to take the partial derivative with respect to x, which is 4 minus 2x, and the partial derivative with respect to y, which is 6 minus 2y. We equate both to 0, so we equate this to 0 and this to 0. So what we get from here is x is equal to 2, and what we get from here is y is equal to 3. And we see that this point is inside D. Okay. If the point is not inside D, we can forget about it, because we are just discussing the function on this rectangle here. Okay. So we see that this is the only critical point. 2, 3 is the only critical point. Okay, so we have to compute the function value at 2, 3. So what do we have? 8 plus 18 minus 4 minus 9. 4 plus 9 is 13. Okay, so here we have 13. And now, but it's not enough. Okay, we also have to look at the boundary, because the absolute extrema could also be achieved at the boundary. Okay, and for the boundary. But for the boundaries, this problem is quite easy, because the boundary here, okay, so maybe let's plot a picture. Also here the situation is very easy. Okay, so we have this is our domain here. Now for the boundary, of course, we will divide it here into 4 cases. Okay, the first case is okay, here the y is equal to 0, and x is from 0 to 4. Okay, so case 1, y is equal to 0, and x is from 0 to 4. So this means, okay, we look at this part here of the boundary. Now, for this situation, because always if we look here or here or here or here, one of the coordinates is a constant. So what we get is just a problem of for a function of one variable. So here the function, call it g of x is equal to what y is equal to 0, so 4x minus x squared. But this you can write as minus, and then you have x minus 2 square of x squared minus, then we have minus 4 plus 4. Now, and actually we have to discuss this function on this interval here, x from 0 to 4. Okay. Now you should observe it. You should observe the following. Normally the boundaries can be much more complicated. Okay, and discussing the behavior of the boundary normally it involves, because again you have here a function which is continuous on this closed interval. So normally what you're going to use is the closed interval method in order to do this. Of course, here the situation is more easy. So you see at the boundary the minimum value or the maximum value is achieved if when x is equal to 2. So in this case you have 4. So the minimum here, minimum value is equal to if I choose one of the boundary points, so 0, and the maximum value if x is equal to 2, which is 4. And now you just do the same for this part, for this part, for this part, and from all the maximum you choose from all those values you see, including this one, the smallest and the largest, and the largest one will be the absolute maximum, the smallest one will be the absolute minimum. But of course, sometimes the boundary here can be quite complicated, okay? And sometimes it's not so obvious how to discuss the behavior of this function here, f of x, y, on the boundary, okay? Because the boundary can be could be some complicated function of this form here. Okay, this could describe the boundary, and then we are led to a problem finding the absolute maximum and absolute minimum value of this function on such a curve. Okay, and it might not be possible to, for instance, of course, in case where you can solve this for y or for x, it's easy. Then you just plug this in, and you have a problem of a function of one variable, and you have some range. For instance, if you can solve it for y, you have normally because the boundary, if it looks if it is closed, then you have some range for x, and then you just replace y by x, and you have some restrictions for x, and you use the closed interval method in order to from last semester in order to find the behavior at the boundary. But the real problem arises if you cannot solve for x and y. Okay? Then you have a general problem which reads you have given a function, you have given a curve, you have to find the absolute maximum and absolute minimum of this function on the curve. And next time we will discuss a method which will give a general solution to this problem. So given a function, given a curve, how to find the absolute maximum and absolute minimum of the function on the curve. And of course, assuming that you cannot solve here for x or y, or you cannot solve easily for x or y. This is the last method we will discuss in chapter 14, the so-called method of Lagrange multipliers. Okay, so I haven't finished this example here, but you can finish it on your own. Okay.